Hello and welcome back. In the next series of lectures, we will look at generative models, especially deep generative models, and in this video we will just take a look at what they mean and what they are used for. So, here is a brief outline of this lecture. So, we have some background to cover and we will see what a generative model is and why we need them, and the types of generative models we will be covering as part of this course. Okay. So far you have looked at problems wherein we have this pairs available x and y, where x is the data, it could be multidimensional data, images, whatever form of data that you have with you, and the label associated with it. So, typical task is a classification task, is yes or no, or like we saw in ImageNet data, you have 1000 classes. So, you have a input x and the corresponding label is given. So, these are labeled data sets, and what we use the deep neural networks for is to learn the mapping from x to y. Okay. So, x is the input and we have a deep neural network which processes that input and outputs a probability score which we threshold and make that into a class label, right. So, this is in the context of supervised learning, right. This is what we have seen. So, another way of looking at it is that the deep neural network defines a classification boundary like shown here in this graph, wherein we have two features, feature 1 and feature 2. This could be some arbitrary numbers after scaling, and the red and the blue dots are the two the data sets or the data points corresponding to the two different classes, and what the neural network does is to determine this boundary, if you can look at it that way, and for which we have access to both the data as well as the label. We have also seen that unsupervised learning, wherein there is no associated label. So, y is not known, right, y is not given, and what we try to do here in this situation is to learn some underlying structure in the data, right. So, that falls under unsupervised learning. Some of the techniques, we can also call them clustering techniques, is what typically used in that context. So, for instance, k-means clustering, wherein we just specify the number of clusters that you hope to find in the data and you end up with labeling accordingly, right. So, in this case we have again two features, and what k-means algorithm does is to, if you think that there are two clusters present in this data, the k-means algorithm determines the center of those clusters, right, and is able to label each of the data points based on the distance from the cluster centers as belonging to either one class or the other. Okay. So, here we are just trying to determine some underlying structure to the data, right, and we do not have access to the labels of the data, we just have the raw data available and we try to find some underlying structure, right. So, in this context their clustering is what we have seen, feature learning or density estimation, all these problems fall under unsupervised learning. So, so part of this unsupervised learning is the density estimation problem. Okay. So, it falls under unsupervised learning, and the idea is to determine a probability density model for your data from which you can draw new samples. Okay. And you determine that probability density, your model density, from the given data density. So, you have given data x. So, this is in this case let us say that you have n data points, 1 to n data points, and so that is basically x I are given, which is an approximation to your, from which you can get an empirical density, right, that is the p data of x. Okay. So, we do not know the true p data of x, for which we require an infinite number of points or all possible x's that you can get your hands on, or that exist, which is not possible. So, you with the data available you can give an empirical density estimate of the given data, but what we want is to determine a model from which we can sample the data points. Okay. So, this is basically generate new samples. So, hence the word generative, hence the terminology generative models, right. So, given probability, so given this data points, so to rephrase, so given these data points, okay. So, again we would not have access to the labels per se, most of the time we just have the raw data and we have the index data, and what we want to do is to figure out or have a model for the underlying probability distribution, which is that is what we want, so that we can draw new samples from it which are similar to our training data. Okay. So, we assume that our training data is representative of the problem that we are trying to solve. Okay. So, in what why is this useful and what do we do with it? So, before we proceed there, we can also there is another way to look at it, which is to say that the generative models learn the joint probability distribution P of x given y, x comma y, whereas the your classifier, for instance, right, you are if you even if you are using a deep neural network to classify data into one of k classes, then the output of the neural network, the scores that are output by a neural network can be interpreted as the posterior probability of the class given the data. So, that is P of y given x. Okay. So, that is not a generative model, right. So, what we actually want is this, of course, these are related through Bayes rule here, right. So, if you have a good model for a prior P of x, then we can actually figure out this. So, this is one way of looking at it. So, what we are this, so this is what is called a discriminative models, right. These are called discriminative models. In the context of classification. So, given what is the probability of the label given the data, that is what a typical machine learning algorithm outputs. So, do most of your deep neural networks that you use for classification. But we do seek something of this sort, where we have where we actually want to model the underlying data distribution, that is P of x typically is what we want to get. So, why do we need generative models? Okay. So, let us say basically we are now trying to look at what kind of applications can they possibly serve. So, the most common application is they can generate new nice pictures, right. You can also use them for image to image translations as shown in these examples, or for instance if you give them labels or outlines, can you generate new data. So, for instance to transform black and white to color. So, you give the aerial map of a city, can give you this this kind of an output like you see in Google Maps, or difference between night and day, here day and it is the same in night time. And if you give labels, once again if you train the model so that if you give it an outline, you can give a output that you seek, since it is a new design for a handbag, if you can think of it that way. So, that is aerial to map, labels to street scenes, labels to facades, and black and white to color. So, these are some neat cool applications that you can think of if you take the generative models, right. So, but the more deeper applications, for instance generating speech from text, right. So, if you have say programs like an automated assistant that responds to your phone call, that is the kind of program that it would require. So, it has some text stored in a digital format and it should be converted to a speech signal in order to respond to a caller, right. So, for raw audio, okay, so you would like to have a generative model if you think of it. Generating sequences of text, so here is one example, but you can if you think of it, a simple application is your autocomplete in your cell phones, or when you are writing mail programs that you are using might have that. So, if you type a few words, you should be able to complete the word or maybe even the sentence. That is also a generative model, right. So, you can, so those are some of the more obvious practical applications of generative models. Okay. Another application would be super resolution, since you are given, so this can think of it in two different ways, like, so here you are given a low resolution data and ideally you want the code to generate high resolution data of the same. You can also think of in image in painting. So, wherein if there are some holes in the images or some damaged areas in the image, you would like to remove that damage. So, if you have a generative model, you should be able to figure out what the missing data is. So, you can think of it for as a data imputation problem also, right. So, these are some of the very high impact or very also some first order application for generative adversarial networks. Okay. So, in the context of medical imaging, this also has its very powerful uses. So, some immediate ones that has also been reported in literature is so for medical image applications, you not only need patient data that has to be obtained with patient consent, and there is a lot of work that has to be done in order to make sure that you are sampling the correct patient population and all that. So, given that it is hard to obtain labeled patient data, right. So, in fact, just obtaining patient data, and then of course, you also have to label them. That's a even more difficult problem, so that you can train a classifier. But if it would be nice if we can actually generate data, that is generate images of anatomy. So, you have let us say brain tumors, right. So, you want to analyze brain tumors or liver tumors. It would be nice if you can have a generative algorithm for generating images of the liver or the brain, even regular anatomy. That will be nice, so that we can actually do at least anatomical level segmentation. Okay. So, that will be a very immediate application for generative models. There is another neat application would be image to image translation. Here it might, this is a little bit complicated from the trying to understand this. So, in many situations, you will have a lot of data for a particular modality. So, let us say CT images of the liver, okay, there are quite a few scans would be easily available. So, large number of even unlabeled data is easily available, right. So, then you can train a model to do whatever diagnostic task that you wish to complete, right. Let us say CT images of the liver, you have used CT images of the liver to let us say segment the liver, right, just to mark the anatomy of the liver. But then the new MRI scanner comes in, and you are starting to take MR images of the liver, which are generally maybe not so easily available, right. So, in order to train a supervised classifier for liver segmentation from MR images of the liver, you need a lot more data which might not be available. Then it will be nice. So, a generative model in this context can be used to convert or translate the MR image to a CT image, use the CT image segmentation model, and then transfer the segmentation mask onto the MR image. So, that is a possibility. So, you have spent it. So, you have trained an expensive model with a lot of data, and a very similar problem comes along. It will be nice if we can use that trained model where you spend a lot of time and resources doing that, right. Of course, this does not work for everything. So, just to for those who are not in the medical imaging field, so you cannot train say CT images of the head. Let us say you have a network that does some diagnostic task on CT images of the head, and then you cannot take MR images of the liver and use that network without, of course, you can do fine tuning and then change, and that is different transfer learning problem. You cannot directly use that network. There is no image to image translation here. You have to use it in the correct context. So, here I am looking at CT images of the liver and MR images of the liver, then it is more meaningful to do that. Of course, these are slightly more research oriented applications, but very high impact if they are solved. So, it is not only in this context, but there are various other contexts in which wherein generative models are used, especially in medical imaging tasks, where they are very useful, and especially in scenarios maybe where you do not have too much data, this might come in handy. So, okay, so what are the types of generative models that we will cover, right? So, we will go into detail a couple of these techniques, not all of them, and we will show how they can be used to generate data. So, most of the applications we will be looking at would involve generating images. Okay. That's the most common application so far. We will not look at text or speech, but just generating images. So, in that context there are different types of generative models. So, this is one of the more highly cited models, actually pixel RNN or pixel CNN. They are based on what are called autoregressive models. Okay. So, they are called explicit. So, they explicitly determine the probabilistic the probability density of the data. Okay. So, they are called autoregressive models because they if you think of an image, you try to generate a particular pixel based on the pixels you have looked at so far. So, if you raster the image row by row or column by column, try to predict a pixel which is in the second column by considering the pixels in the first column of the image. That's the basic principle. So, it comes under autoregressive models, and it gives you an explicit density, which is basically the neural network itself. The deep neural network is the density is modeled using a deep neural network, right. So, just to give you an idea, so for instance, if you are working with some simple data, you can model that data using a, let us say, a Gaussian, right. So, your density would be something of this sort. Okay, right, something of this sort. So, instead of this, we will just have some f of x, which is basically nothing but a deep neural network. Okay. So, in most of the applications, most of the generative models using deep neural networks, the idea is to model p of x with the deep neural network itself. So, the network is the model. Okay. So, another class of generative models which also explicitly determine density is the latent variable models. One of them, the more highly cited work, is the variational autoencoder. So, we will cover this in the next few videos. So, variational autoencoders, again they are, it's called variational autoencoder because there is a it's an approximate way of determining the density function, right. So, that's one, and we will see why it is called latent variable model when we actually look at the algorithm in detail. Of course, the most studied model in the recent past is the generative adversarial network. Okay. Here we do not explicitly model the density, the probability density, instead we just sample from it directly. Okay. So, the neural network outputs a sample, right. So, directly outputs a sample. So, that is the idea behind GANs, and again it is a deep neural network and primarily has been used for generating images. So, in fact, I have not seen any application otherwise, but it is the more popular applications are for generating images, and there have been very recent successes for generating images of human faces, and they look very realistic. So, you can look them up if you do a search. So, we will primarily focus on VAEs and GANs. Okay. So, variational autoencoder and generative adversarial networks will be the two generative models that we will focus on. So, to summarize, so generative models try to model the underlying data distribution. So, data is basically your training data. So, which is we want to figure out this, we want this where x say training data, right. So, that we can draw samples from the probability distribution which looks like your training data. So, that is how you should interpret generative models. So, once that is once you have that model, then there are a lot of applications that are possible. That is the ones I showed you, and they can also be used as classifiers. So, they can also be used in the context of classifying. Of course, it is much more straightforward to, if you have labeled data, it is much more straightforward to train the classifier directly using a deep neural network. So, but this is, it is a possibility to do that using the model that you have figured out. Okay. So, We will continue with this in the next few lectures. We will look at variational autoencoders and generative adversarial networks. Thank you.